Moving on in the notes, let's finally do an example here. Find the critical points, local max or local mins, and saddle points of z is equal to 4xy minus x to the fourth minus y to the fourth plus 4. So we're going to go through the steps I outlined in the previous recording. The first step, just like in Calc 1, is to find the critical points. And so technically a point in 3D has the z component, but we're just going to go ahead and say these are critical points in terms of x and y. And so just some lingo there to pay attention to. So to find the critical points, you need to remember that you need to take the partial with respect to x, set it equals 0. Also, you need to find the partial with respect to y and set it equals 0. So doing that here is not so difficult. Here what we get, having x be a variable and y held fixed, we're just going to get 4y. So derivative of x is 1 and the rest is treated as a constant out front with a constant multiple rule. Then the partial with respect to minus x to the fourth is 4x cubed. The minus y to the fourth is just a constant. When you take the partial derivative, 0 plus 4 is 0. So we get something that's not so bad. And then a weird thing you might notice is maybe, you can factor out the 4. This is kind of in the style of what we would have done in Calc 1. And then it's like, wait a minute, it's a y and an x. What's going on? Totally can't solve that. Well, just leave that for now. Remember, you have to also find when the partial with respect to y equals 0. So, just go do that. It's a similar derivative as before. And then, yeah, maybe you want to factor out the 4. Technically, you could cancel get rid of the 4 and divide it by 4 because it is a constant. Do not do that for variables because you're going to miss some solutions to those equations, but technically I could get rid of it. So now what? See, that one depends on x and y as well. So what we have here with the and, the way that those are connected is a system of equations. So you might be thinking, oh yeah, that's easy. But notice something. We are not dealing with a linear situation. So when you have two linear equations and two unknowns, you can solve that for sure. These are not linear because you got the cubes in there. And it's in terms of two variables. So this is where the algebra can get a little tricky. I'm going to give you some that can be solved algebraically, but you're going to have to notice something, and it's not always going to be the same thing every time, unfortunately. So the method or what we notice in this one is not going to be the same every time. So anyway, let's look at these and try to see what's going on. Well, one thing I can see is that in the first one, I can solve for y. It's just going to be x cubed if I want it to be. To divide by that 4 and do that. And this one I can solve for x. So, that's helpful. And potentially. So I did that here and I get y equals x cubed and again x equals y cubed. So then in this form, maybe you can be inspired to do something. And notice you can substitute in here one into the other, and actually doesn't matter which one. Personally, I like to do things in terms of x if I can because that's more familiar, so let's just plug in x cubed for y in the other equation. So this is a technique we use from solving a system of two linear equations. And it turns out we can kind of use some reasoning from knowing that, but not every time when you have this nonlinear situation. So that's helpful because then I get this equation x equals x to the 9th. Now here's where you again have to be really careful. You never want to cancel out the variables when you do this because you're going to miss the solutions. Remember, we're trying to solve for x. And so just like from before, what you want to do is have some sort of factoring going on. So it makes sense to bring over the x on the left-hand side to the right-hand side and see, oh, I can factor out an x and take that approach. So now you have the solution x equals 0, and you'd miss that if you just canceled it and got rid of it before you noticed that. And then the other factor, x to the 8th minus 1, is actually a perfect difference of perfect squares, is what we call it. In other words, it can be factored in x to the 4th plus 1, x to the 4th minus 1. Or you can just set it equal to 0 and solve for x, but don't forget that when you take a root that's even of both sides, then you gotta throw that plus or minus in front. Okay. So we do that and we get some x's. That's good. We're getting somewhere on here where we're getting critical values. We have the x coordinate, and then easily we can find the y that go with those. You at some point had this little equation y equals x cubed is the easiest one to use, but you can plug it into either equation that you found from up here and just figure out what the corresponding y's are. Doing that, you get the critical points of 0, 0, -1, -1, and 1, 1. So that was more work, and it's a little trickier than in the 2D situation from Calc 1. Now we get our more complicated second derivative test to determine if these are local max or mins or saddle points. So one of the big deals here is we need to find big D. And so look at all the stuff it's got in it. It's got the partial, double partial with respect to x, double with respect to y, and then the partial x, y, or y, x, whatever your choice is. So you got lots of side work to do. You do have the first partial with respect to x. Some people like to just do these at the beginning, knowing that they're going to do the second derivative test. I didn't do that in these notes because, you know, you'd be like, why is she doing that? So that's fine. You don't have to do that, but just a heads up if you want to be efficient, and that way you can. So now just take the other partial with respect to x, and I see that I'm missing some notation there. I'll throw that in before I post the notes. If I write it in all these boxes, it'll reveal. So anyway, this is a partial with respect to x, and it's just simply -12 x squared. Do the partial with respect to y. Again, we had missing the prime there, I think. Yep. So I'll throw that in. Oh no, it's there. Sorry. F sub y. Thinking of 2D land. So the partial with respect to y, take that partial with respect to y again, you get -12y squared. And then we do need the one from partial with respect to x, then y, or vice versa. Either way, you get 4. So it's worth your while to put this all together as big D, which is given here, and simplify a bit if you can. So our simplified expression is 144 x squared y squared minus 16. So now with the critical points, you're going to plug in. And at this point, like in Calc 1, it's kind of nice to organize this in a table, both for me to grade and for you to be organized and get all your answers. Also, then you don't have to restate your answer because it's in table form, and I can tell what your answer is from that. So it's efficient. Plugging in big D with the 0, 0, you get -16. And really all we're trying to get out of big D is its sign. So if you want to be kind of lazy at some point and not actually calculate the number, that's okay. But be careful that you're actually bringing it through far enough that you can tell its sign, for sure. So it is negative. Do this for the rest of the critical points. Get its sign here at this point, 144 minus 16 for the critical point at -1, -1. Was like, well, yeah, obviously that's going to be positive. I don't even need to bother doing that subtraction. So once you get there, then we start breaking this down. If the D is greater than 0, then we have to look at the sign of the partial, double partial with respect to x. But if it's less than 0, it's negative, then we can just conclude there's no local max or min, which means it's a saddle point. You do have the work for the second partial with respect to x up high here somewhere, wherever that was. Oh, right here, because I didn't have it labeled. And so just plug in there with your critical value. It turns out only the x coordinates coming into play here. And then get its sign. So it's negative in both cases, which means that they're both local maxes. And then you're finally done. And these are long problems, just like they were in Calc 1. I restated the answer down here, just to be clear. However, if you have a table set up this way and it's nicely labeled and whatever, then that's good enough. Maybe for the circle or something, I don't know. Now what does this look like? So this is kind of abstract, just doing all the algebra and everything, but for each of these I did plot them so you can see what's going on. So here we have two local maxes that you can see kind of in the green and purple area, and then the saddle point is between them. So this would be like a mountain pass if you're going hiking and you can see the other side, but that's it. So I will stop this recording and then do another example on the next recording.